So today, uh, good morning to all of you. Today we will start our discussion on radiation. This is the fifth module. So first of all, we have to define what is radiation. What is radiation? There are actually two concepts, two school of thoughts on the definition of radiation. The first concept is radiation is the propagation of electromagnetic waves. And the other concept, the second school of thought, is radiation is the emission of energy particles known as photons. So both these definitions are acceptable to the scientific community because one concept doesn't contradict the other one. So first of all, we will uh, define the concept of black body. What is a black body? A black body is one which will absorb all the radiations falling on. So it is a perfect absorber of radiation. At the same time, it is a perfect emitter of radiation. It will be emitting maximum amount of radiation from its surface. So now there arises a question. When a black body absorbs radiation and when it emits radiation? When a black body absorbs radiation, when does it absorb the radiation? So a black body absorbs radiation when the temperature of the surrounding is more than that of the black body, and it emits radiation to the surrounding when the temperature of the black body is more than the surrounding. So now we should know how much amount of radiation that will be emitted by a black surface. So for that we define a term called emissive power. Emissive power of a black body. Emissive power of a black body is defined as the amount of radiation emitted by the black surface per unit area. Amount of radiation per unit area. So normally for a black body, this will be a function of its wavelength and temperature. This is given by a law known as Planck distribution law. So Planck distribution law here, which gives the emissive power of a black body as a function of wavelength and temperature. So this is given as an equation. EB means the emissive power of the black body. C1 by lambda to the power 5 into e to the power C2 by lambda t minus 1, where the values of C1 and C2 can be obtained from the data, HFT data. So it is obvious that this emissive power is corresponding to a particular wavelength of radiation, right? But normally a black body emits radiation of various wavelengths. So in order to find the total emissive power of the black body, you have to integrate the Planck equation from 0 to infinity with respect to lambda. So when you integrate, you get an equation like EB is equal to sigma T raised to 4. This is known as the Stefan-Boltzmann law. And sigma is its value is a constant. Its value is 5.67 into 10 raised to minus 8 watts per meter square Kelvin raised to 4, which is known as Stefan-Boltzmann constant. So this is the emissive power. Emissive power means the amount of radiation emitted per unit area. So in order to find the total amount of radiation, that is the heat emitted by a black body at a particular temperature, you have to multiply the above expression sigma T raised to 4 by the surface area. So you get the amount of total amount of heat emitted as QB. Q means heat emitted by the black body as sigma into A into T raised to 4 watts. So we know that every surface will be emitting radiation based on its temperature, surface temperature. So there will be other objects around a particular object. So there will be exchange of radiation. One body is emitting radiation and the other body is emitting radiation based on its temperature. So we are interested to find the net exchange, heat exchange between two surfaces. So in that case, Q net can be found by using the expression sigma A into T1 raised to 4 minus T2 raised to 4. For T1 and T2 are the surface temperature of two bodies. If a surface at a temperature T1 is surrounded by a fluid having a temperature T infinity, then Q net will be calculated as sigma A into T1 raised to 4 minus T infinity raised to 4. I hope that you understood these concepts. Okay. Now we will take a break. Okay. Yeah, we will resume it. Now we have to explain the visible spectrum. You might have heard of visible spectrum. So the visible spectrum is actually a domain contains radiation of various wavelengths ranging from 0.38 Armstrong meter to 0.78 Armstrong meter. So I have actually shown a graph here. This is nothing but the graphical explanation of the previous Planck's distribution law. So Planck's distribution law gives the emissive power as a function of the wavelength and temperature. So here I have plotted the emissive power of the black body as a function of wavelength in the x-axis and the temperature as shown in the graph. So for various temperature, I have drawn the emissive power. See, for example, for 100K, you can see that the wavelength range is very high. That is starting from 0.9 to 2.5. That is beyond the visible spectrum. So, and for 200K, it is shown here, and 300K, and etc. And what you can observe is, if you are log ഞാൻ അയച്ചിരുന്ന ലിങ്കിനകത്ത് ക്ലിക്ക് ചെയ്താൽ പോരെ പിന്നെന്താ സൈൻ ഇൻ അപ്പൊ നിങ്ങൾക്ക് ഒരു പാസ്വേഡ് ഒക്കെ ഇല്ല, നിങ്ങൾ അത് വെച്ച് സൈൻ ചെയ്ത് കയറിയാൽ മതി. ഓക്കെ. So now we will talk about the visible spectrum. The visible spectrum, that means there is a domain of wavelength starting from 0.38 micrometer to 0.78 micrometer. Okay. So here what I have done is I have plotted the Planck equation for the emissive power as a function of wavelength and temperature. Okay, so you can see that for various temperature, 100K, 200K, 300K, I have plotted for various wavelengths. Wavelength is shown on the x-axis, and you can see that for each temperature, the emissive power increases first and then decreases. So it increases to a maximum and then decreases. And for temperature 200 K also the same pattern, 300, 500, etc. have drawn. So for every temperature, you can see that the emissive power is becoming a maximum. So at this point, the emissive power is maximum, right? And for maximum emissive power, there is a corresponding wavelength that you can get from the x-axis. Okay. So similarly, for every temperature, you can have a maximum emissive power and a corresponding wavelength. And we call this wavelength corresponding to the maximum emissive power as lambda max. Lambda max means the wavelength corresponding to maximum emissive power. And you can see that the wavelength corresponding to the maximum emissive power is shifting to the visible region as temperature increases. As temperature increases, you can see the slope of this line. The maximum, the lambda max shifting to the visible region as temperature increases. So this is to be understood. And there is another important thing that we can observe is the product of the lambda max and the corresponding temperature. The product of lambda max and the corresponding temperature is always a constant, which is having a value 2.9 millimeter Kelvin. So this equation is known as Wien's displacement law, and this equation is used for finding the temperature of distant objects. Okay, so you can use this equation to find the temperature of the surface of the sun, right? Surface of the sun. So you can measure the value of lambda by using an instrument called radiation pyrometer. By using the radiation pyrometer, you can find the value of lambda max, and putting in this equation, you can find the temperature of that surface. So you can find the temperature of even the surface of the sun can be used by this equation. So now we will have a break. ഇപ്പോൾ ഒരു ബ്രേക്ക് കഴിഞ്ഞു, ഇനി വീണ്ടും റെസ്യൂം ചെയ്യും, ഉടനെ റെസ്യൂം ചെയ്യും. ഹലോ ഹലോ So again, I am repeating the visible spectrum. Visible spectrum is a domain of the range of wavelength varying from 0.38 micrometer to 0.78 micrometer. So here what I am doing is I am just plotting the Planck distribution law equation. So emissive power in the y-axis, wavelength in the x-axis, and the various temperature are shown here in this graph. And you can see that for 100K, the wavelength is very high. It is of the order of 0.9 micrometer to 2.5 micrometer. As temperature increases, you can see that the wavelength range also is decreasing. And for every temperature, you can see that the emissive power is increasing first and reaching a maximum and then decreasing. This maximum emissive power point is very important. There is a peak point, and there is a corresponding wavelength. For a particular wavelength only, you get the maximum emissive power. And this wavelength is known as the wavelength corresponding to the maximum emissive power, and it is denoted as lambda max. And you can see that lambda max is shifting to the visible region as temperature increases. Here we are having a very important law called Wien's displacement law. If you take the product of the lambda max and the corresponding temperature, you can see that the product lambda max and temperature is always a constant for all the temperature, and that constant, the value of that constant is 2.9 millimeter Kelvin. 2.9 millimeter Kelvin. This is the Wien's displacement law. Using this equation, you can find the temperature of a distant object. Okay? So you can even find the temperature of the surface of the sun. And you can measure the lambda max by using an instrument called a radiation pyrometer. By using radiation pyrometer, you will be able to determine the lambda max value. And if you put that value in this equation, you will be able to calculate the temperature of the surface of the sun. So any distant object surface temperature can be measured by using this equation. That is the importance of this law, Wien's displacement law. Now I am taking a short break. So the next topic, next point we have to discuss is the radiation shape factor. So what is radiation shape factor? Suppose there are two surfaces, A1 and A2. There are temperatures T1 and T2, having emissivities epsilon 1 and epsilon 2. See, here I am defining a term, emissivity. Emissivity is defined as the radiation by a real body to it is a ratio of the radiation by a real body to the radiation by a black body. So it is simply comparing the emissive power of a real body with a black body. And when there are two surfaces, there are different temperatures, they will be exchanging radiation. Okay, or they are exchanging heat radiation. And we know that the Qnet is equal to the EB1 minus EB2, right? Or EB1 into its surface area minus EB2 into its surface area, right? So here we should understand one thing. The radiation emitted by the first surface may not be reaching the second surface. All the radiation that is being emitted by the surface 1 may not be reaching the other surface 2. So only a portion of the radiation emitted by the first surface will be reaching the second surface. Similarly, all the radiations that are emitted by the second surface are not reaching the first one. So only a fraction of that radiation that is being emitted by the first one is reaching second one. And similarly, only a fraction of the radiation emitted by the second one is reaching the first one. So this fraction, is called the radiation shape factor, and this is denoted by F12. F12 means the radiation emitted by the portion of the radiation emitted by the first one that is reaching the second F21. F21 means the portion of the radiation emitted by the second body and reaching that reaching the first. So when you
third body.
take the net heat exchange between these two surfaces, we can write it as Q net is equal to A1 into sigma into T1 raised to 4 into its emissivity epsilon 1 into the radiation shape factor F12. Similarly, for the second body that is being emitted by the second body and reaching the first one can be calculated as A2 into sigma into T2 raised to 4 into its emissivity into its radiation shape factor F21. So this is the net heat exchange between these two surfaces. This is the actual net heat exchange by these two surfaces. So sometimes we can assume that the emissivity of both the surfaces are same. That is, epsilon 1 is equal to epsilon 2 is equal to epsilon. So Q net will become epsilon sigma into A1 F12 T1 raised to 4 minus A2 F21 T2 raised to 4. And here we can assume that both the temperatures T1 and T2 are same. If both the temperatures T1 and T2 are same, then there won't be any heat exchange. So the Q net is equal to 0. And when you substitute these values in the previous equation, you get epsilon sigma into A1 F12 T1 raised to 4 minus T raised to 4 minus A2 F21 T raised to 4 is equal to 0. Here epsilon, sigma and T raised to 4 are constant. So you get a relation A1 F12 is equal to A2 F21. This theorem is known as the reciprocity theorem. So using this theorem, you can convert the shape factor of one body to other in terms of the shape factors of other bodies. So that is the importance of this theorem, reciprocity theorem. Okay. So this, and you can find the radiation shape factor for various configurations by using charts that is given in your data. Okay. So we will have a break and then we will So now if you have any doubt, you can send message to me so that I can answer it. You can send message, no problem. So next concept is the radiation between parallel plates. This happens in many situations, especially in the case of storage vessels. Storage vessels that will be a double-walled vessels, and between the walls, vacuum will be kept or some insulation may be kept. So there will be radiation between these two walls even when vacuum is maintained between these two plates. And how to calculate the amount of radiation between these two plates? So for that, we have to use the analogy we used in electrical engineering. Here there are three parts, three components. One is the first plate, which is having a temperature T1 and which is having an emissivity epsilon 1 and a surface area A. And the second component is the second plate having a temperature T2, having an emissivity epsilon 2 and an area A2. and in between there is a space. That space also is offering a radiation resistance. So this is this is a function of the shape factor F12. So you can see that there are three resistance offered by the first plate, the second plate, and the space in between these two plates. So we can calculate the radiation resistance offered by a surface by using an expression 1 minus epsilon divided by epsilon into A. Okay, that means the radiation resistance offered by the plate that can be calculated as 1 minus epsilon divided by epsilon A. And the radiation offered by the space between these two plates is calculated as 1 by A1 into F12. 1 by A1 into F12. So the total radiation resistance is obtained as 1 minus epsilon 1, that is for the first plate, 1 minus epsilon 1 by epsilon 1 into A1, plus 1 by A1 into F12, plus 1 minus epsilon 2 by epsilon 2 into A2. Suppose the surface area A1 is equal to A2 is equal to A, then you can get the total resistance R 1 by epsilon 1 minus 1 plus 1 plus 1 by epsilon 2 minus 1. So here F12, the value of F12 is 1 because whatever radiation that is emitted by the first will be reaching the second. Similarly, whatever radiation emitted by the second will be reaching the first, because there is no way of escaping of radiation from this space. So that is the reason why the value of F12 is 1. That is full amount of radiation emitted by one surface reaching the other one. So that the value of this fraction F12 is 1. So when you add all these values, you get an expression 1 by A into 1 by epsilon minus epsilon 1 plus 1 by epsilon 2 minus 1. So the heat exchange between these two parallel plates is obtained as the radiation potential divided by radiation resistance. What is radiation potential? Sigma into T1 raised to 4 minus T2 raised to 4. All divided by the radiation resistance is 1 by A into 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So finally you get an expression for Q net, that is the radiation heat exchange between plates as sigma A into T1 raised to 4 minus T2 raised to 4, all divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So this is it's a very important expression. This is widely used in radiation calculation. Now we will introduce another concept, that is radiation shield. Radiation shield is where we use a radiation shield in order to minimize the radiation exchange between two plates. For example, I told you for storing low temperature or high temperature fluid, we may use a double-walled vessels. So double-walled vessels, the space between these two walls will be filled with vacuum. And if you can keep a plate in between, that plate is known as radiation shield. And you can see that if you keep one plate, there are calculations, but that is not included in your syllabus. If you keep one plate in between the main plate, that means if you insert one radiation shield between these two plates, you can reduce the net heat transfer by half, 1 by 2. Okay. Similarly, if n number of radiation shield in between the main plates T1 and T2, then you can reduce the that heat transfer between these two plates by 1 by n plus 1. So when you keep one radiation shield, you can reduce it by 1 by 2. 1 by 2 means 1 by 1 plus 1. Similarly, if you keep n number of radiation shield between these two plates, you can reduce that heat transfer by 1 by n plus 1. So this is the concept of multi-layer insulation. Multi-layer means multi-number of radiation plates are introduced between the main plate. Okay, so I think by this I am stopping the discussion on radiation. So you can go through all these notes, and I will send. I'm actually recording the presentation. That also I will be sending to you. You go through these things, and if you have any doubt, you please call me. Thank you.